Hey everyone, welcome to our first lecture on one of the ways that chemists like to start thinking about molecules in three-dimensional space. The way that we talk about this is by talking about conformers. So what are those? Let's get some definitions out so that we can be on the same page with what we're talking about here. So when we say conformer or conformer, either way is correct. What we're talking about is a conformation. And that might seem a little bit obvious, right? But I want to break that down a little bit to tell us what that even means, right? A conformation is when a molecule, right, is going to conform to some specific thing, right? Whatever that is. But that's the idea, is that we're conforming. And in the context of organic chemistry, that's going to be certain different types of shapes and alignments of bonds and orbitals. So we are going to favor certain different types of conformations over other ones because of stability. Basically, everything comes down to in chemistry whether it's stable or not. So that's something that we are going to consider when we look at these new conformations that we're about to draw. So again, why does this matter really? The reason that it matters is because we've been getting used to looking at these molecules on the page, but that really doesn't do justice to what they're looking like in reality, because we've seen these molecules and they just kind of sit there on the page, but they're not frozen in time in the same way that we like to see them in our textbook. What we see in the textbook is just a snapshot, but all of these molecules have other things that they can do. So they will definitely be doing things like rotating. And that's what we're going to talk about today. They can rotate freely. They can spin in space, the whole molecule. They can bend, and they can even vibrate. So we're not really going to be worrying about most of these, but we will talk about rotation today and a little bit more throughout the semester. This is really important because the alignment that you can achieve by rotation sometimes will allow reactions to happen or not happen at all. So that's why this is a little bit of an important topic for organic chemists. So when we talk about seeing these things in three dimensions, I want to give us a little bit more information about that and how we're viewing it, how we're representing it. So I've got our good friend here, hexane, and I've just drawn it out in our skeletal form, but we have to remember that it's not flat. It looks like it's going to be flat, but it's not. So think back a little bit to Gen Chem. We didn't stress this in the Gen Chem review portion, but there are plenty of different atomic shapes that, molecular geometries that we can have depending on what the different type of molecule is that we're looking at. So I've listed three here that are important for organic chemistry. We have tetrahedral, we have trigonal planar, and we have linear. And those correspond to our three different hybridizations. So the tetrahedral is sp3, trigonal planar is sp2, and linear is sp. So these are the geometries that we need for OChem. The rest of them you will not see, and it doesn't matter. But for this part of the unit especially, we really want to focus on the tetrahedral nature of these sp3 hybridized type of molecules. That's what we're going to be working on in the rest of this video. So want to start out with an example of methane, right? So I've drawn methane there. That's the formula for methane, and I can draw methane like this. This is kind of a simple, like Lewis structure style drawing of methane. But then there's the three-dimensional way to draw methane, and that would look something like this. Now I'm going to introduce these kind of strange, funny-looking bonds that you may have seen on some of our homeworks, on things on the exam. I don't think there were too many on the exam, but you may have seen these before and been like, I don't know what that is. And fair dues, because you would have no idea what it is. It's a tool that we use in organic chemistry to try to show perspective when we're drawing on a flat piece of paper, right? So what I'm holding up right now is a simple model of methane. Here in my hand, I have the center of this sort of tetrahedral structure is labeled in black for carbon. There are certain types of colors that we use as standards. So standardly speaking, carbon is always black, and then hydrogens here on the end of each of these points are labeled with white. So you can see that when I manipulate this in space, that it's absolutely not flat. It doesn't look like kind of an X shape or a plus sign like the Lewis structure does. It definitely has this sort of three-dimensional drawing to it, or three-dimensional feel. And so we want to put that into the drawing. So what I've got here are two things that I will highlight here in different colors. We've got this type of bond here, and that's what we call a wedge for what might be obvious reasons, because it has kind of a wedge shape to it. So there's the wedge, and then the counterpart to the wedge is the dash. And so what these do, again, they're just meant to represent positions in space. So when we're talking about looking at this methane molecule and kind of really piecing it together, when I'm looking at these hydrogens here that I'm labeling in green right now, those we've drawn as a normal flat line. That means they sit in the plane of the page, just like we would be expecting them to. But then if we go and look at the wedge instead, that kind of has that wedge shape, like it's almost coming out at you. So that's what that is supposed to represent, that the wedge is sticking just out in space. You can imagine it popping out of your computer screen or your page of paper, right? So the other way around that is the dash, right? If we have something that is coming out of the page, the dash is the thing that is going back behind the page. So imagine that that's kind of the reason you can't see that bond, the reason that it has those dash marks is because it's kind of like hidden behind a screen. You can sort of see it, but it's not in the same plane as that screen. So that's what these sort of funny shaped bonds are here to represent. And you're going to be seeing them a lot more as we move forward in the semester and as we continue on learning about these conformers. So let's take a look at something a little bit more complicated than methane. So here's, gee, I forget what this is, 2, 4, 6, 8. So this is octane, it's not hexane, but it doesn't really matter what it is. I just wanted to show what it might look like to fill in a bunch of these hydrogens with wedges and dashes. So again, this is a lot of work, hence why I'm not drawing it out in real time here. And we pretty much won't do this unless there's something else here that's not hydrogens. This is the same idea as drawing out all the hydrogens in a Lewis structure. It takes too much time, so we typically don't do it. But I wanted to put this in here to highlight a point of how it is going to make it nice for you to draw it and nice for me to look at it and read. So just as a little point of drawing etiquette, let's say. Anytime we have these kinds of straight chains where we have carbons that kind of point relatively up toward the top of the page, and then we have some that point relatively down toward the bottom of the page. Let's do those in, let's see, pink, I guess. Hopefully you can tell the difference between these colors. If you're not sure, that's totally okay. But these ones that are kind of pointing down toward the bottom of the page, you'll see that for almost all of them, I've drawn the wedge and the dash pointing downward toward the bottom of the screen or page. And for all of these purple ones, I've drawn the hydrogens going up, the wedges and the dashes pointing up toward the top of the page. So I fell off a little bit here, but that's kind of the way that it's going to be nicest for them to look and draw to look right. If you draw them in basically any way, I'll be able to understand, but this is my preferred method. If you want to make my life easier, try to draw them like that. The other thought that I wanted to talk about here, looking at this sort of larger molecule, get rid of these arrows really quickly, is again, like I said, it's really overkill to draw this. And you might sort of say, well, does it really matter what's going on with these hydrogens here? Because, I mean, they're all hydrogens. Do we need to see where they are in space? Do these ones matter? Does sort of the spatiality of it matter? So I'm just putting this in as a little seed question for some of our next lectures. Sometimes the arrangement in space of certain things doesn't really matter. So when that's the case, we're going to start practicing just ignoring it and only paying attention to the places and times when it does matter. So stay tuned for more on that. Let's get a little bit, dip some toes into the water of that on this next slide and look at this slightly smaller, more reasonable molecule where you can see now I didn't draw in all of the wedges and dashes. I just drew in one, right? So I have some questions here to help us to get started on this. And one of those is, what does this look like? What does that wedge dash really mean? So what you'll be able to see now that I'm holding up to the camera is a small model of this compound, and I will arrange it in a way such that it lines up with what we are seeing on the screen as well. So again, all of the black bonds represent carbons. This one that is tipped out here in red that I'm holding right now represents oxygen. So this is where our OH group would be. So what I'm looking at here is just showing you that, okay, if I align this sort of carbon bonding framework in the plane of the page, right, or in the plane of your sort of screen, this O is kind of pointing out toward you, okay? So that's really what this quote unquote looks like in 3 dimensions, something like this. And we'll talk more about what you can do to model in a few minutes, so stay tuned for that. But I also want to talk about what's implied here. So this goes back to all of the other things that we've talked about with drawing organic structures and having things that are implied. Implied, if we have this OH coming out as a wedge, that means we also have to have a dash. There's always going to be a wedge and a dash. So the dash must be a hydrogen, right? And again, we didn't draw it in because we didn't need it until we started considering the arrangement in space here. And similarly, you could draw a wedge and a dash here at this carbon. I'm just drawing them really small so that they can fit in. There's 2 hydrogens there, but again, we don't need those just yet. So we're going to go ahead and remove them. So not forgetting about those implied hydrogens. Those are very important. So why does it matter where that OH group is? In this case, it does matter. So that's why I've drawn it in with the wedge dash. I'm indicating it because it does matter. And we'll talk more about why this is a really big deal coming up in the next couple of lectures. So stay tuned for that. But basically, if you have this one with the wedge compared to the other one with the dash, they can be very similar, but they can actually behave in totally different ways. That's why it's really important, and it has a lot of implications to things like medicine. So stay tuned for more on that. So now it's time to practice, right? We've got some vague ideas about what these things look like in 3D, but I promise you, it probably won't be easy for many of you. So we want to do a lot of practicing with it so that we can manipulate this in 3D and kind of have a little bit of practice and exercise using 3D thinking. So you're like, Grace, okay, whatever, chemicals can be 3D, that's fine. You don't go in and manipulate chemicals, you know, individual molecules with your hands the same way that I do, right? So why do you need this? What's going to help you about this type of lesson that you can take outside of chemistry when you never look at another chemistry textbook again? And what I'll say to that is that you're going to have to think in 3D a lot of times because life isn't 2-dimensional, right? That's really, I think, where the biggest lesson comes in here. I'm also thinking about this for a lot of you who may be interested in going into like veterinary medicine, right? Something like that, especially if you are going to be doing any kind of surgeries, the things where you have to think about how things in, you know, physical bodies are arranged. Even, I'm sure there's a lot of ways that this can come in agriculture, right? I like to think that a cornfield is just flat and there's no contours or dimension to it in other ways, but I'm sure that totally plays into how water runoff occurs and what's getting more or less hydrated, right? So there will be other places in life and in your future careers where you may need to think in 3 dimensions. So it may not look anything like what you're about to do, but hopefully this will help practice that skill. So what we're going to actually do for chemical 3-dimensional thinking is something called the Newman projection. So the heck is a Newman projection? So this is the mysterious Newman projection. I've said it that way because there's a bunch of question marks there. When you draw your Newman projections, which we will do together in this video, you won't put question marks there, you will put different chemical groups there. So this is named after some guy, Newman, who did his work at one of my former institutions, the Ohio State University. You don't need to know that. What you do need to know is what the heck you're looking at here. So this is supposed to be a different way to represent a view of a carbon-carbon bond. But instead of kind of looking at it from the side like we normally do, we're actually looking down it much like you would look down a telescope. So you can see that I've got my little cardboard tubes of science here. And if this represents a carbon, right, we're just picturing that bond as being this sort of tubular shape. You can look at it side on like this. That's how we've been looking at them all this time. But if we just rotate it, then we'll be able to see down it much like a telescope. So that's what we're looking at here when we're looking at a Newman projection. And so when I say it's a carbon-carbon bond, that implies that there are 2 carbons here. And so I'll give you another view of this in a moment when we talk through the process of drawing the Newman. But this is going to be, this kind of center point right here represents the carbon atom number 1, right? And then the second carbon is a second circle that is behind this one that represents carbon number 2. So that's the kind of idea here, is that we're looking down them so exactly perfectly that they're lined up. You can't actually see the one that's behind carbon number 1, but it's still there. So the other thing that we'll show a little bit more about as we go along is these branches that are coming off here, and the highlighter is going behind the circle, which is a little bit inconvenient, but those branches represent the other bonds from carbon number 1 to its substituents and carbon number 2 to its substituents. So the idea here that these substituents that I'm highlighting in red show up at the front of this circle shows that direct bond to carbon number 1. And these other ones that are kind of, they get cut off by the circle, right? They're cut off by that circle because they're not bonded directly to this carbon. They're bonded to the other carbon, which is behind that. So their bond angle is a little bit obscured. That's what we're trying to show here. And then what does this tell us? We can sort of understand what we're looking at now, but what does it tell me? This is a useful tool for chemists to understand where specific atoms are in space. And we can kind of get that just from wedges and dashes, but more so, the Newman is going to be even further useful if we want to think about how these molecules might rotate. So we said that molecules are always able to rotate. Sometimes they might want to, sometimes they might not want to. Again, this is all based on stability. So this will tell us whether we do want to rotate or maybe we don't. So let's look at the 2 types of Newmans that you will be seeing in this class. They mean the same thing. They're just 2 different conformers of the same thing. So I kept my question marks here, right? So what I'm looking at is just a simple rotation, right? Let's give these a couple of names so that we can talk more specifically about them. When we have this form over here, where we have kind of bond to the front, bond to the back, bond to the front, bond to the back, bond to the front, and so on and so forth, they're kind of evenly spaced out. So we call this a staggered conformation. And then when we have this version on the other side here, where they're right next to each other, we call that eclipsed. Much like the moon can go in front of the sun when they're exactly aligned, we call that an eclipse. So that's what's happening here. We're showing them as slightly off from one another, just so that it's clear what's what, but they are perfectly eclipsed in reality. So these 2 things are both possibilities, right? When we're rotating, if I were to highlight, let's say I'm going to do a red question mark here, a green one here, a blue one over here, and then I will make just one of these ones on the back, purple, as an example. So let's say that I did a rotation around the bond that we're looking down here, and I didn't touch the front carbon. I'm going to keep these color labels the same on our front carbon. So if we go around, say clockwise, it doesn't really matter. We start at red, we go to green, and then we get to blue. So that's the same order that we have here, exactly. But now we've rotated that back carbon so that that purple question mark could be in a couple of different places. We don't actually know, but let's say that I did a rotation that goes about 60 degrees that way, counterclockwise. Then the purple question mark would be up here and is kind of aligned with the red question mark. So that's how these 2 things are interrelated, by doing simple rotations of 60 degrees at a time. You'll go to a staggered, then an eclipsed, and then a staggered, and then an eclipsed. So what's the difference between these? Does it matter? Why do we care? Which one do we prefer? So one is better than the other here. And I will go ahead and tell you right now that we most certainly always prefer the staggered conformation. Now, why is that? It has to do with personal space, essentially. Atoms with their electrons don't like to be that close together, right? Remember, electrons repel one another. So the electron clouds don't like to get close to one another. And what happens when you have, let's get a different color here. What happens when you have groups close together like this, even though they're separated by one carbon, they still have a little bit of interference of their electron clouds. So they're not happy with that. They want to spread out and get to the most, nice, normal, spacious conformer that they can. And that happens to be always our staggered conformation. So if you are asked which one is more stable, which one is lower in energy, it's going to be the staggered conformation. To look at this on a chemical model can be really, really helpful. So again, more on models in a moment, but just to show what we're looking at, my thumb and forefingers are pinching the 2 carbons that represent the circles right now. And if you're seeing this and you're like, I don't understand, I can't see the circles, we want to just turn the model like so. And then if you line your eye, I always have to close one eye to get a good look right straight down it. You can sort of start to see these kind of Y shapes emerge. And then if you just imagine a bigger circle there, that's what we're looking at with the Newman. So in order to convert a staggered to an eclipsed, all you're doing is rotating one of the carbons by 60 degrees at a time. That's it. And so that's what we're going to practice doing, but we're going to practice doing it on paper. So now let's learn how to draw these Newmans. So again, if you felt like you've been a little unsure about what I'm talking about here, hopefully doing this translation from a regular skeletal structure to the Newman will help you out. But again, this is some very visual stuff. So what I would like to recommend for you all is some kind of a modeling tool. Now I've got these are actually pretty crappy old chemical models that I don't really think you need to spend your money on. If you got some friends who have a kit from past years of taking chemistry, definitely see if they will lend it to you. But if you don't have that, we got other options. What I would recommend is coming up with something that will be able to be flexible and you can build and change things if you want, and also be cheap and readily available. So my best 2 options for you are, both involve toothpicks, or like coffee sticks. If you go to the coffee shop and they've got those little coffee stir sticks, those are good too. So taking some toothpicks and then whatever you've got around, I would recommend things like grapes, or go get some, splurge on some gummy candy at the Kroger or whatever. And then you can kind of build these little models for yourself so that you can manipulate them in space and rotate them. I will absolutely allow the use of any kind of home-built modeling tool on the exam. Plus, if you make it out of gummy candy, then you can eat it later. So that's one option. The other option that I have been maybe already showing you a little bit is this kind of toilet paper tube version, where if you just cut a toilet paper tube in half and then stick some, coffee sticks. I've got color-coded toothpicks here, which is nice so that you can remember which groups are what. If you put them together like so, then you can just rotate one and the other, and that will help you view your Newmans without having to spend money on a chemical modeling kit. You don't need that. So let's start with just how we're going to draw these without a kit, and then I'll recommend that you practice with the kit, because that will probably help you get more used to it. And again, you'll be open to use whatever tool you have kit-wise on a quiz, exam, homework, any of that. So without a kit, we start by drawing a circle. To me, that's the hardest part. You may or may not agree, but drawing a nice circle is not my forte. That's why I've got this nice auto-corrected circle from the iPad. And then once you've got your circle, we have to draw that kind of Y shape. Let's go back up to the top here for a second to look at these sort of Y-shaped Newman projections, right? There's kind of a right side up Y or an upside down Y, or maybe in the case of this eclipsed version over here, we had 2 upside down Y shapes, right? We need to decide which way it goes, if it goes up or down. So in order to do that, we're going to do what I call putting myself into the Newman projection view. And the way that we like to draw that in chemistry is by defining what carbons we have here. I want you to look from 1 to 2, and I will always try to make that as clear as possible in the directions. I want you to sort of fly yourself in there and look from carbon 1 down to 2. And so to indicate that, I will draw an arrow like so to say, okay, that arrow, that's where you're looking. And I also like to draw what usually turns out to be a really creepy looking cartoon of an eye, that's actually pretty good, all things considered, to show that like, that's the side view of somebody's eye that you are looking right straight down it. So that's where you want to be thinking about being in this Newman projection drawing. And again, it'll be a lot easier when you try this with your model kit. So we're going to say, okay, this carbon here in the middle is carbon 1, carbon 2 is behind there, and we're just going to ignore that for now. So we want to decide how to draw the Y shape on carbon 1. And you're probably like, I got no idea, Grace. How would I know that? You don't yet, but I'm going to tell you. So when you've got your eyeball looking at that carbon number 1, what you want to look for is where the straight line bond is, right? That's attached to carbon 1. So just for perfect clarity, I'm going to draw in our implied dashed hydrogen there. So at carbon number 1, we have the wedge OH, we have the dash H, and then we have this here, which is a CH3 group. You can label it like that if you like, or you don't have to. And the CH3 group is the thing that has the kind of normal looking straight bond that we've been seeing this whole time. So this is the bond that I'm looking for. Let me highlight it with a different color. Go for pink. And that is below where my eye is, right? So if we think about this arrow, right, as kind of a plane of our vision, it's sort of below the plane of our vision. That means that we want to draw the sort of straight up and down part of our Y going down because it's below, okay? So if the straight line bond is below our plane of vision, we draw it straight down on the Newman projection. So I'm going to redraw this and move our 1 so that it looks a little bit nicer, like so. So now we know that the base of our Y is pointing straight down and that the kind of 2 prongs of our Y will be facing upward, like so. Once you know where that straight line bond is, you can decide about the other 2 that they just have to go in this kind of Mercedes-Benz shape. They're always going to be shaped like that. These angles are always going to be about 120 degrees as far as just drawing. So we decided how the Y shape is oriented, right? And we'll do this again for the second carbon, but we're just going to finish up with carbon number 1 first. And then the next step is filling in all of our branches. So we have these 3 branches here, right, that in previous Newmans I've labeled with question marks. Now we need to fill them in, because if you leave them unfilled, that means CH3. Sometimes that's right, but it might not be right. So always, always, always make sure you clearly label the ends of your Newman projections so that you're not accidentally implying a carbon that's not there. So maybe one of the easiest ones to start with is this CH3 down here, right? Because we said that because that's sort of pointing down and it's below the plane of our vision, it's pointing down here in the Newman projection. So we already know that. So that CH3 goes there. Now the slightly tougher part is where to put the OH and the H. One of them has to go here and the other has to go there. But which one goes where? To explain it a little bit quickly, what I like to do is just pretend that my eyeball aligns with the eyeball that I've drawn on the slide there. And then if I think about that, the way I have to turn my face, the OH would be kind of pointing outward and toward the right side of my face, whereas the H is pointing in toward the, behind the screen, and therefore it would be pointing to the left-hand side of my face. Again, that's the really, really quick explanation that may not make that much sense to you. And if it doesn't, that is totally okay. Just get some kind of a modeling tool to help build with and look at that, because that will be really straightforward. Or if you don't have a model kit, you don't have any candy on hand or toothpicks or whatever, that's totally fine. I can show you a method that I like to do that only uses your own body, right? And then you can kind of get a more visual 3-dimensional feel for this by just physically turning your body in space. That requires a lot of arm flailing on my part, so I'd prefer to save that for another time. If you're interested, we can talk about it and I can show you in office hours. So just let me know if that sounds like something that would be helpful to you. So there we go. We are halfway done with this Newman. We've filled everything in on the front carbon. Now the last thing we have to do is just repeat the same steps for the back carbon and fill those in as well. So if we go back to thinking about where our eyeball is and where our plane of vision is, like so, if we are looking for the straight line bond on carbon number 2, right now that's the only one that's drawn in, it's right here, and it's pointing above our plane of vision or upward. So we want the straight line on the back carbon to be pointing up. Again, notice that I'm not completing the line, I'm not completing it to the center of this circle because it's supposed to imply perspective that it's further away and obscured by carbon number 1. So that is going to be the straight line bond here that's on carbon 2. And if that's the case, that tells us that our Y shape, the base of our Y is pointing upwards, so it's actually an upside down Y. And we can fill in the other carbons like so. So with that Y shape in place, now all we have to do is label. So we can look back again at this position here. That was a CH3. Again, you can label that however you like. And since we decided that is the one that is the flat regular bond, it's pointing straight up, we know that that must be there. But then the question occurs, what's left? There's nothing else at carbon 2, right? Or is there? Don't forget that there are implied hydrogens at carbon 2 that also have an implied wedge and a dash. But in this case, since they're both hydrogens, it doesn't matter which one is on the wedge and the dash because they're the same. And on our Newman, it doesn't matter which one is on the left and the right because they're the same. So you should be careful when you have different substituents that you make sure you get the correct ones on the left and right side. But if you have a case like this with 2 hydrogens, it doesn't matter as long as you've got the thing that is in the plane of the page, that kind of straight line bond. As long as you got that correct, doesn't matter where the other 2 pieces go. So that is how we draw a Newman projection. And it is, again, I will say this a million times, a very, very visual skill. So you should practice it a lot with whatever works the best for you. The last thing we're going to do with Newmans is just practice rotating them around, because this, like I said, is what they're useful for. It tells us whether we want to rotate or not. So when we are trying to rotate here, we can do that to get to new conformations if we want to. And when we do that and get a new conformation, we can compare the two against one another to see what their relative stability looks like. So for instance, I'm going to bring back in this Newman that we just drew of the previous compound. And then we'll do a little rotation of it. So what I'm going to do is I'm going to hold the back carbon totally constant. I'm going to label these here. I'm going to label this CH3 with pink and these 2 hydrogens with pink here. And I'm going to, again, just literally copy it over. But now we're going to change, we're going to do something with these front carbons, right? So what I'm going to do here is do a 120-degree rotation of this front carbon. Let's go clockwise. So what I'm going to do is start here at this OH, and I'm going to turn the whole carbon 120 degrees that way. So this little curly arrow will show I'm doing a 120-degree rotation. You don't have to draw this kind of arrow if you don't want to. But that means that the OH is going to move 120 degrees clockwise to take the position of where the CH3 is right now. And same goes for the rest of them. The CH3 will move 120 degrees to supplant the hydrogen, and so on and so forth. So I like to think about this as, you know, turning a big old bus wheel, if you like that, or again, just rotating your model kit, either way. If I move the OH from this position here down to here, and then move everything else following the same pattern, the CH3 goes this way, and the H goes that way. Now we've done a 120-degree rotation of our Newman projection to get to a different conformer. So what does this mean for us? What good does this do us? How can we tell which one we like better? Again, it's an issue of personal space. So when we think about the biggest, bulkiest groups here, we have little hydrogen atoms here in blue and pink. Those are not really very important. So I'm going to erase their highlights for now to say, oh yeah, they're there, but it's literally the smallest atom you can get. So we're not really concerned with it. The other bigger atoms that we have here, I'll highlight in blue. We have a CH3 there, and we have an OH down here. So we kind of just want to get an idea of where their personal space is. And so to be super clear, I'm going to erase all of these marks on the previous one and color code in the same way so that we can get an idea of which one is more stable. Okay, so what you want to look for is when they're just getting close to one another. We have a special term for this called a gauche interaction. You won't need to know that, but it comes from the French, meaning left, I believe. Just means that they're next to each other, right? So I'm drawing these kind of weird overlapping parentheses to say, hey, like those, that's kind of like a picture of the electron cloud of this CH3 group and the electron cloud of this OH group, that they're getting kind of close. They're sort of overlapping there, and they don't like that. That's not super stable. But we have the same problem over here. We have this CH3 and this CH3 here. So those are some interactions that just have these bulky things kind of getting a little too close to each other. So we want to basically decide on which form will minimize those the most so that we can achieve stability and all of these little atoms can have their personal space just the way that they want it. So in this case, we have kind of one, let me draw it here. We have kind of one neighborly interaction there. And this CH3 group down at the bottom is fine and happy. It's not bothered by these little tiny hydrogen atoms. And in the other form, we have kind of one personal space neighbor interaction there. And now the OH is down at the bottom by itself. It's happy, it's got its personal space. So this one is a pretty difficult one to choose from to begin. So don't worry if you can't really tell which one should be better. It's very close. So the kind of go-to rule that I'll give you for these Newman projections is anything that is carbon hydrogen based is usually going to be bigger, just because there's more hydrogens right here on this methyl group. Like so, just one on the OH is not so bad. But if you have a whole bunch of carbon and hydrogen, those are going to be really bulky and have a big electron cloud that doesn't want to get near other big bulky carbon hydrogen electron clouds. So based on that logic, we're going to say this one over here on the right hand side is worse. It's a little bit close to call, I will say, but that one is worse. So we're more stable here where we started. So I'm going to label this one as the more stable conformation. And so depending on what I ask you for, I might ask you to choose between the two, which one is more stable, or ask you to draw a rotation and then decide which one is more stable. That will be a feature of your homework coming up for this week. And I will just say, since this one was a little bit close to call based on the relative size of OH and CH3, I will make the ones that you have to choose between much more clear cut, so that you're not like, well, I don't know, I don't really have an idea of the size of an OH group. I don't want to try to make this tricky. I will try to make it as straightforward as possible to say, oh, okay, this one is obviously bigger than the other one. So all that to say, there's a lot going on here, and you're probably going to have plenty of questions and things to think about, ways to try to decide what way to study this is going to work best for you. So with that, when I come to the review and practice part of the lecture, there's a lot, you just have to do Newman's. That's what you need to work on for now, because it's such a strange new thing. You've probably never had to think about things in this way, especially things that you already can't see, and now we're trying to look at them in a different way. It is going to be tough, and it might be very challenging to you, especially if you don't feel like you have a good sense of how to 3D visualize. So please do not wait to start practicing this and asking me questions on it, because it may be difficult. So practice drawing the Newman and rotating them, and then thinking about stability as well. But those two are the big first things that you need to be worried about. And then if for whatever reason this clicks in your brain and you feel pretty comfortable with it, feel free to move ahead. That's totally fine. The next couple of lectures, we're going to start introducing cyclohexane and how it's not a flat hexane ring, or I'm sorry, a hexagon ring. It's actually what we call a chair. So stay tuned for that. And we're going to be learning a little bit about stereochemistry, which explains why we care so much about where atoms are in space. Again, a lot of new content today, and this lecture was a little bit longer than some of the other ones. So please go back and watch through it again if you need to. Please, please, please hit up the discussion forum and ask questions there. Email me your questions or stop by office hours. Take care.